Assalamu alaikum. Welcome to lecture number 19 of digital signal processing. In the last week, we have discussed very deeply regarding the discrete time Fourier series and discrete time Fourier transform. We looked at these two techniques in much detail by looking at some special cases also for our intuitive understanding, as well as we have done various numericals and tried to solve them by using multiple approaches to get our concepts clear. So in this week we are going to cover discrete Fourier transform in much detail, and also after discrete Fourier transform we will try to expand our discussion with fast Fourier transform, which is the same like a discrete Fourier transform, but the difference is speed and its computation algorithm. So if you understand the concepts of a discrete Fourier transform, it will be very easy for you people to learn the fast Fourier transform. And as you all know that discrete Fourier transform and fast Fourier transform are one of those robust techniques which can analyze any real-time signal, and it can be applied to any signal whether it is periodic or aperiodic. So I would like you people to pay your complete attention on these topics, as these topics are very important as far as DSP is concerned. In the discrete Fourier transform, we will first discuss the time domain sampling effect in frequency domain. However, we learned this concept in various parameters such as Nyquist criteria, as well as through some special cases. But here we will look at this concept in another way, and obviously in a very different perspective, yet it support the concepts we already learned in the previous lectures. So this concept will strengthen our concepts regarding the Nyquist criteria. In the second part we will discuss what will be the frequency domain sampling effect in time domain. Then we start our discussion with a discrete Fourier transform and its analysis equation as well as synthesis equation, how we can analyze real-time signal with the help of DFT, and we will try to look some numerical problems to understand this concept in much detail. Then after conventional formulas of DFT, we will look at one of the robust formula of DFT, which is in the terms of matrix, that is known as matrix formulation of DFT, which is very easier to solve on paper pencil also, and it is also easier to implement on some processor or control system. Then we will look at some of its aspects in terms of its computational speed and the number of computations required in that DFT calculation, and we learn different parameters related to it. So now let's proceed to the lecture number 19. So here is the quick review of discrete Fourier transform which we have started the last week. So as we are more interested in analysis of real world signal and we know that most of the real world signal are continuous in nature and as well as aperiodic. So if we look at the technique which can be applied to such type of signal, so we can say that CTFT is the technique which we can apply to analyze any real-time signal. But the main thing is we actually want the frequency domain view of that signal, so we can make decisions on the basis of its frequency domain view. We can process that signal and we can refine that signal, or we can do any intelligent task related to that signal in the frequency domain. But the main problem is when we are going to analyze this type of signal which is continuous and aperiodic in nature, so first of all we need to convert that signal into discrete time signal, because our machines, that are processor and memory, is finite. So there we actually want that real-time signal which is continuous and aperiodic in nature, to be converted into discrete and aperiodic, which is the nature of the real world signal. So actually we convert our continuous and aperiodic signal into discrete and aperiodic signal. So you can see with the help of pointer I am highlighting the nature. After the conversion of signal into discrete time signal, our signal become discrete and aperiodic. So we can say that we can apply DTFT technique to analyze this type of signal. But as we are more interested in the frequency domain view of that signal, so we can process this that signal more efficiently. So when we look at the frequency domain view of DTFT, then we know that it is a continuous and periodic spectrum. So such type of signal will have a continuous and periodic spectrum. Again, the same limitation, that our processor and memory is finite, so we cannot process any continuous time series. So frequency domain series is basically continuous and periodic, so we have to convert that this continuity into discreteness. So when we look at these different parameters, then we came to know that this one, which is TTFS, is the technique which is discrete and periodic. So actually we need some technique to convert the frequency domain spectrum from continuous into discrete. So again the problem is okay, fine, we are going to convert our continuous and periodic spectrum into discrete and periodic spectrum, but when we apply again the digital to analog converter to that signal to come back in the time domain, because we are interested in the time domain view of signal after processing, so we came to know that the time domain view is again discrete and periodic. So here discrete is no issue, but periodicity is the issue. Periodicity is such an issue which is same as you can recall the concept of sampling theorem. There if we sample the signal on improper rate, then actually aliasing occur in the frequency domain. So here we are doing discreteness in the frequency domain, so due to that discreteness periodicity occur in the time domain, and if we do not select the correct sampling rate in the frequency domain, this periodicity will be such a major problem to us, because when the signal is converted into time domain and the periodicity factor or parameter do not reconcile with the with our standard or desirable task. So for example, you can say you have a speed signal of 2 seconds, and the after conversion, that is output of digital to analog converter, if the periodicity changed to 1.5 second, then you can imagine your signal is actually overlapped, which means you may lose your information which was present in that signal. Again, another case, if the periodicity will become 3 second, so it means that 2 second is the original time of that signal, and after 2 seconds there is 1 minute silence in which there is no informative or no, you may say, no data for which is useful to you. So it means that 1 minute duration is complete useless. However, it occupies some memory location because obviously that has some values which may be zeros. So the major problem is basically periodicity in the time domain. However, continuity was a problem, but we solved that issue with the discrete sequence of frequency domain. But due to that discreteness, periodicity arises in the time domain. And if that periodicity is not handled carefully and efficiently, it will create a serious problem and our original information will be deteriorated and we will not be able to retrieve that information in any way. So there a need of some robust and efficient algorithm arises which is fulfilled with the help of a discrete Fourier transform. This technique is one of the robust technique which you can say is the combination of DTFT, but the frequency domain view of DTFT is continuous and periodic spectrum. But with addition of DTFT, it also performs frequency domain sampling so that the frequency domain view of your signal is discrete and periodic. And if you see the chart, the discrete and periodicity is written here. So in against we will get a discrete and periodic waveform in the time domain also. However, this is not the DTFS, it is DTFT, because DTFS is used to analyze discrete and periodic time domain signal into frequency domain. However, we are now converting continuous time frequency domain view into discrete time frequency domain view, due to which we are getting this discrete and periodic signal in the time domain. So DFT is basically the combination of DFT plus frequency domain sampling in simpler words. So this, however, this technique is performed with a special algorithm and equations, but for our understanding purpose we can say that it is the combination of DTFT plus frequency domain sampling, and not the frequency and not just the frequency domain sampling, the optimum frequency domain sampling. And we will see what is the optimum rate of that frequency domain sampling. So after the optimum frequency domain sampling we will get discrete Fourier transform algorithm. In this slide, we are going to learn why discreteness causes periodicity. As we know that both of these are the transform pair, once we are discretizing our time domain signal, so the periodicity occur in the frequency domain and vice versa. If you perform the discreteness and frequency domain, you will get periodicity in the time domain. So why this happened? Very interesting question, and answer is also very interesting. So we are going to look at the answer in this slide. Suppose you have signal x of t which is continuous in nature and aperiodic as well. You can imagine it as a real world signal which are continuous in nature as well as aperiodic. So suppose you have such type of signal. So if you wish to look at its frequency domain view, then you know that the continuous and aperiodic time domain view have a transform pair of continuous and aperiodic frequency domain view. So whatever the frequencies are present in this signal are going to reflect in this frequency domain spectrum. So basically it is a generic spectrum in which these frequencies are present in this signal. Now we are going to discretizing this continuous and aperiodic signal. So with the help of impulse function we can actually discretize this continuous time signal. So actually we are going to multiply this original signal with this impulse signal to get the discrete time signal of our original signal. So in this way our continuous time signal is discretized. Now you can notice, and we have studied this also, the impulse function or the discrete and periodic impulses have a frequency domain view which is also discrete and periodic in nature. Recall the special cases we have learned in the last lecture. We have learned there, if we have a discrete and periodic time domain signal, then its transform pair will be discrete and periodic in the frequency domain. So according to that concept, the frequency domain view of this type of impulse series of impulse signal is discrete and periodic impulses. So what is actually happening? I am going to add one more concept here which is related to the concept of convolution we have learned. Basically there is a transform pair of convolution which is multiplication. Multiplication and convolution are transform pair. If you are going to multiply two signals in time domain, then convolution occurs in the frequency domain and vice versa, which means if you multiply the spectrum in frequency domain, the time domain signal will get convolved. This is very important concept and it is applied to most of the DSP algorithms, which is convolution and multiplication transform pair. So this transform pair is actually working in this case also. How? You have this continuous and aperiodic signal and you are multiplying this continuous and aperiodic signal with this impulse train, obviously a scaled version of this impulse train, and the scale or magnitude depends upon the original signal. So here you are multiplying two signals to get your desired signal. So actually convolution takes place in the frequency domain, and the frequency domain view of this signal is this continuous and aperiodic spectrum, and the frequency domain or view of this impulse train is yet another impulse train. So these two frequency domain representations are actually get convolved with each other because multiplication is going to happen in the time domain. So when these two frequency domain representations or frequency domain signals are convolved with each other, as a result we will get this spectrum. So you can see that this spectrum is actually convolved with each of these impulse function to yield this type of frequency domain representation. You can notice that your original signal has actually these values of frequency present in it, but after discretizing this signal you will get the spectrum which is periodic in nature. So it means you have to consider only the unique part of that spectrum, and you know that unique part has a range of minus fs by 2 to fs by 2. We have learned the concept of periodicity for discrete time sinusoids. There we looked at the concept the legitimate range of frequency is minus half to half or minus fs by 2 to fs by 2. So basically the unique pattern lies somewhere here. It is the copy paste version of this central spectrum, which occurs due to the multiplication of two signals in time domain and the convolution of two signals in the frequency domain. So you can see, and it is very clear to you that in this way discreteness causes periodicity in the frequency domain, because you are discretizing your signal in time domain and actually periodicity will going to happen in the frequency domain. Now in this slide we are going to learn more about time domain sampling effect in frequency domain. Obviously this concept will back the theorem which we studied earlier, the sampling theorem or the Nyquist criteria, which tell us about the efficient rate of sampling in time domain. So you can look at the figures. Here you have an analog signal which is continuous in time, and you have another signal which is series of impulse train. So actually you are going to discretize this continuous time signal with the help of this impulse function. And how you will achieve? You will multiply both signal. So you have a block, you can say this block as a multiplier, and you will apply two signals, which is one of your original signal and the other is the impulse signal. And actually these two signals are multiplied with this multiplier block, and the result is y of t or the output signal, which is the discrete version of the original signal. Obviously the impulse signal has some specific time period, or you can say the sampling time which you require to sample this analog signal is basically the sampling time or TS of this impulse train. So after this specific interval your signal will be discretized. So at the end you will get this kind of output. So here is the frequency domain view of a spectrum, in which you can see that different cases are assumed. as per Nyquist criteria. Nyquist criteria actually tells us the rate for sampling of analog signal, and the statement of Nyquist criteria is basically Fs is greater than or equal to twice of Fmax. It says for proper reconstruction of signal, you must sample the analog signal with a sampling frequency which is greater than or equal to twice of the maximum frequency present in the analog signal. So here we are considering three cases. First case is of oversampling. There we select Fs as greater than twice of Fmax. The second case, critical sampling or perfect sampling, where the Fs is equal to twice of Fmax. And the third case is one where aliasing occurs actually, which is Fs is less than twice of Fmax. So you can see due to the discreteness, this spectrum actually repeat itself after certain time interval. However, the unique portion or unique information lies in this central part, but due to the discreteness, these replica occurs. So if we are going to separate this unique part, we can easily do it in this picture, which is the case of oversampling, because these replicas are far away from each other and we can easily identify the unique pattern. So this is the case of oversampling. However, this oversampling requires higher sampling rate, which means greater number of samples. Greater number of samples means you will require more memory and more processing time and higher speed of processor for such type of processing. So however, this case is beneficial as it provides the unique spectrum and we can easily separate out or identify the unique part. However, if we do the sampling at a critical sampling rate, which is twice of Fmax, you can see these replicas are actually very close to each other and actually touch the boundaries of other replica. So this is the very critical case in which you have to analyze the unique pattern very carefully. However, the replicas are not overlapping with each other. You will easily identify the unique pattern by using some smart techniques, but you must be very careful while doing it when you are sampling the signal at critical sampling rate. You can see it and observe it from the figure also. But the last case is useless, or you can say that the frequency domain information is actually overlaps. So you can see that replicas are basically overlapped with each other and this part is actually where the aliasing occurs. So if you have this frequency content present in the signal, it will take some other value and show up as a lower frequency component because of this aliasing issue, and this aliasing is basically due to the undersampling of the signal, and you can observe from the frequency domain view also by doing the undersampling of signal the frequency spectrum actually overlap, so you may lose and you will definitely use the unique information of spectrum of that signal. In the previous slide, we have learned the time domain sampling effect in the frequency domain. Now in this slide, we are going to learn the frequency domain sampling effect in time domain. Obviously, in any domain we are performing any task, there must be its effect in the other domain. So whether we are doing sampling in time domain or whether in frequency domain, there must be certain effects that arises in the other domain. So here we are going to discuss the frequency domain sampling effect in the time domain, and this slide will support the concept of DFT, because we claim that the frequency domain view of signal was once continuous in nature, and that continuity was actually a problem, and we have to discretize that frequency domain view. So basically we are doing frequency domain sampling, and there we claim that due to this sampling actually periodicity arises in the time domain. So in this slide we look at this concept with various plots and try to learn this concept. So here you can see you have a time domain signal which is already converted into discrete sequence or discrete time series, because you can see it is represented by L. So and you can see at y-axis it is represented by x of n, and the signal is discrete in nature. So the signal, a continuous time signal, is already converted into discrete time signal. And we have learned in the previous slide that due to converting this continuous time signal into discrete time signal, we actually face the periodicity in the frequency domain. So you may say that this is the view of its frequency domain. As you can see, your time domain representation is discrete as well as aperiodic, so its frequency domain view must be periodic and continuous in nature. So this is the generic representation. This representation does not belong to this graph particular time domain waveform, but it is a generic waveform. So actually what happened, we are going to discretizing this frequency domain representation, because we have a limited memory and limited speed processor, finite speed processor, so we cannot process this continuous spectrum actually. So we are interested in a discrete spectrum of which has certain sequence or series. So when we discretize this frequency domain view, then actually periodicity occurs in the time domain. And you can see if this is your original signal which has some values, you can actually count these values: 1 2 3 4 5 6 7 8 9 10 11 12 13. So these 13 points are basically the values, and we are representing these values with the notation capital L. So capital L is basically denoting the time domain samples of our original waveform. Now we are going to sample our frequency domain representation. So obviously this will be achieved with certain number of samples, and we denote that number of samples with capital N. Okay, fine. Remember, capital N is used to represent the frequency domain samples, and capital L is used to represent the time domain samples. So when we discretize the frequency domain representation with number of samples denoted by n or n number of samples, then actually periodicity occurs in the time domain. So our this original waveform will repeat itself after the time interval which is equal to n. So this is very interesting and important concept. L is basically the number of samples of actual time domain, and n is basically that value after which your signal repeat itself. So you can see that actually the number of samples or useful samples which are not zero are these up till there. You can see the pointer 1, 2, 3, 4, 5, 6, 7, 8. 8 samples are basically useful while other are zeros. So if these 8 samples will not reconstructed properly, then actually we lose the original information and actual information. However, this is not the prime purpose of processing. The prime purpose of processing is to actually refine the original signal on various parameters. So if we lose the original signal, then no need of processing. So actually we want to retain these number of samples. So now if we are going to sample this frequency domain representation, again if we do not choose the proper sampling rate in the frequency domain also, we will ended up with a mess in the time domain. And what will be the output in the end if we do not sample the frequency domain representation correctly? You can see when n is selected as less than L, the original signal, which is this signal, is actually repeating itself, but it is also overlapped with each other. So we are actually lost the original information. And if we are going to consider the case where n is greater than L, which means the number of samples in frequency domain are greater than number of samples in time domain, then we are actually getting these idle values which are irrelevant or unnecessary, but these are coming as an output, and obviously we have to store these values somewhere, and definitely it will take some memory also. So these two are not the realistic case where n is greater than L. However, we can consider this case n is greater than L, but there is disadvantage. We have to spare some memory for useless data. But the second case is the worst case where we actually lose our original information. So the best case is when n is equal to L. So by that critical sampling, we actually get the original information in the end, and also our memory will not be occupied with the useless information. So the best case is where n is equal to L. L is the time domain samples and n is the frequency domain samples. So again a question may arise that how we are going to select this number n or L, because it is very critical, and if we do not select it properly, then things will ended up with mess. So here is the answer. DFT is the technique which actually selects the optimum rate by itself, which is discrete Fourier transform is the version which performs actually DTFT plus frequency domain sampling at the optimum rate, and that rate is basically n is equal to L.